Very good morning to all of you. Sir has told me everything about me. So the wisdom of the past is the light of the future. With these words, I would like to extend my heartfelt thanks to the organizer of this incredible conference. It's an opportunity for all of us to get into the very important dialogue, that is bridging heritage, the ancient research in the advanced technologies. So it's a reminder for us that the technologies we have developed or we are developing, the cutting edge technologies, these are deeply rooted in the knowledge, experimentship and the craftsmanship of our ancientors. So today I am going to talk about one of my work, that is synthesis of titanium aluminum intermetallic by MASHS. MASHS stands for Mechanical Activation Self-Propagation High Temperature Synthesis technique, and it study its microwave absorption property in ceramic matrix. So first thing it comes in our mind that what is synthesis? Synthesis is very simple process by making or creating new material by adding some substituents or elements or compound. This is the basic concept of science and technology. It allows us to create different kind of material based on their properties and all that, for stringent requirement and all that. So the term material synthesis might be sounds new, but it is as old as our our human civilization. So our ancientors are the first material scientists. They prepare different kind of material with the resources available to them. So I'm going to highlight some of the ancient techniques as early material synthesis. First one is metal smelting. This is the most transformative process in human history. Thousands years ago, the ancient civilization discovered that when we heat the clay and stone, when we clay and stone, we get the important at high temperature. We can extract the important valuable material from that. So the copper is the first metal to be smelted. The second one is alloying. Actually, my font and everything has changed in this laptop. The second one is the alloying. Alloying is also very much important synthesis technique. The ancient civilization came to know that when they add the two materials together, two metals together, they get the third metal that is much superior than in the properties of their constituents elements. So bronze was the first alloy was discovered with a mixture of copper and tin. The third one is pottery and ceramics. It is also as ancient as our civilization. They used the ancientors made useful tool using the clay itself only. Then glass making. Glass making is one of the historical achievement in ancient time. It's involved the melting sand with the other materials like soda and lime ash at high temperature. The molten glass could be then shaped and cooled into the solid form. This is very much stringent technique because a lot of parameters need to be controlled. So at that time people came to know that these things we need to take care, like the heating time or many things are there. So then here stone tool making. Stone tool were made by striking stone like flint and create sharp edges. So this one was also a very useful invention by the human beings. Then fire and pyrolysis. Ancient civilization used the controlled burning to transform the materials. So pyrolysis is the thermal decomposition of organic materials in the absence of oxygen. So in ancient time, people used to create charcoal by burning wood in different kind of these, as mentioned in the figure, this kind of bhattis, and we can say. So material synthesis have a very rich history. So the field of material synthesis revolving from the rudimentary technique to the sophisticated and advanced modern techniques. So these are some glimpses that in prehistoric era, discovery of natural material, then development of metallurgy and ceramics, then advancement in chemistry, refinement techniques, then in early modern periods, the birth of modern science. Then in 20th century, the polymers, semiconductors, composite, nanotechnology has come in the picture. And in 21st century, we are doing the advanced multifunctional smart material with strategic applications. And parallelly, we are also doing the application of modern technique for material synthesis following ancient roots. And as we are listening from since tomorrow in this conference, so we are working on that novel kind of material for strategic applications. So here I am talking about intermetallics. So intermetallics are very much similar to the alloys. So the only difference is the bond is that between intermetallics are partially ionic. And one of the important properties that is distinguished intermetallic from alloy, that its crystal structure is completely different from its constituent elements. So there are two types of intermetallics, that is stoichiometric and non-stoichiometric. Stoichiometric intermetallic have fixed composition, and non-stoichiometric have range of the compositions, means the composition is not fixed, we can vary their composition. This leads to very important properties to the non-stoichiometric intermetallics to the stoichiometric intermetallics. So we are talking about titanium based intermetallics. So titanium based intermetallics offers many advantages. Thus they can be used in aircraft because of high strength to weight ratio, high corrosion resistance, low specific gravity, non-magnetic properties. Of course they are offering with high specific strength, and they are biocompatible material, and they are having good fabrication ability. So titanium based intermetallic can be used in many kind of application, including aerospace, medical, industries, and other special applications such as marine, sports equipment, and ultrasonic welding. Now we will talk about our material, that is titanium aluminite. It is also a class of non-stoichiometric intermetallic. So this is having the properties that is lightweight and high strength. Two phases of titanium aluminum intermetallics are received attention: alpha phase and gamma phase. And this is also this material can be used at high temperature application also. So this is the beauty of this material. It can be used in many applications like aircraft, space vehicle, industry, gas turbine, combustion engine exhaust and electric train, structural component, and high temperature furnace. So there are many synthesis methods have been reported in the literature for the synthesis of this titanium intermetallic, that is forging, metal induction molding, additive manufacturing, vacuum casting, spark plasma sintering. Every method has their unique advantage, but they are come with some limitations also. That is, these are the high energy consumption, time consuming, high equipment cost, non-uniform heating, and complexity in controlling the parameters, because it is very difficult to get the pure phase of that kind of intermetallics, because sometimes we get the mixture of that, so that material will not be useful for the required applications. So we have adopted a unique technique for the synthesis of titanium aluminum intermetallics, that is MASHS, as I told earlier, that is mechanical activation, self-propagation, high temperature. It is a combination of two techniques. One is mechanical activation and second is self-propagation, high temperature. So the beauty of this technique is it's a unique effective method for preparation of advanced material, and the enhance overall reactivity of the material. Then we will get pure material in very much less reaction time, and it's energy efficient also, and it has less environmental impact, and we get good yield also this product. So the procedure involves the selection of suitable material, then mechanically activated that material, and then compaction of that material in reaction vessel, and ignite or heat the material up to that temperature for self-ignition. Then we will get our final product, and we process the ingot and collect the powder. So this is the method that first we will precursor, we use titanium powder, aluminum powder with AR grade, and then mechanical activation will be done in planetary ball mill with the optimized rotation period and rotation speed. Then we transfer this reaction mixture into cylindrical vessel and put the vessel in the shaft furnace, and then ignite this powder. Then we will get this kind of ingot. This kind of ingot we will get. Then we process this ingot and sieve with the desired particle size range, and we will get our final powder. Then we will characterize it by the various characterization techniques like XRD. So the XRD spectra reveals that there is no it confirms the formation of titanium aluminum phase as a major phase, and no residual phases are present there. Then also morphological study confirm the irregular shape of the powder, and EDEX microgram confirm the presence of titanium aluminum. Then elemental analysis and particle size distribution analysis have also been carried out. Then when we are using this powder for different kind of defense applications, we need to develop some kind of composite material by using this material. So we made a ceramic composite by using the synthesized titanium aluminide in alumina matrix. So this is also a very long process. First mixing and milling and drying and granulation to make the powder compatible for our applications. So I will conclude that we have established a unique synthesis technique for synthesis of titanium aluminide, and the developed process has capability scaling up also. We can synthesize 2 or 3 kgs powder in one batch of reaction. Then the coating composites have been formulated by dispersing the powder in different concentration of that powder in ceramic matrix, and application and testing on strategic platforms successfully carried out. So this is open for that. Can we explore the synthesis of strategic or advanced or multifunctional material by the Vedic route also? Thank you so much.